Hello everyone. Today we will talk about phylogenetic trees. In general, as you know, trees are very useful in order to describe and summarize data. And now we can also introduce you phylogenetic trees as an evolutionary tree to show how it can be useful in order to categorize species based on their similarities, differences in different aspects, like for example, physical or genetic characteristics of them. There are different types of phylogenetic trees. Some of them are rooted, other ones are unrooted. Like for example, this one. This one is unrooted because we don't see where is the initial point. But for other trees that you can see that here is the initial point, here is the initial point, and also here we have an initial point which we call root. So these are rooted ones and this one unrooted. And in unrooted trees, sometimes the distance of these lines are important. And for determining about the length of these lines, there are different algorithms, different formula in order to calculate them. But in case of unrooted ones, we don't care about the length of these lines. We care about the categorizing these items only. And of course, in unrooted ones, we are categorizing them as well, but they are useful because the length of these lines can be important in order to understand how different they are from one another. Now here's an example related to rooted phylogenetic trees. As you can see, we have an initial point which we call root in trees, and we have leaves here, like suffix tree, as we introduce these parts as leaves. And what does it mean? It means that from the beginning you categorize these species into this part and, for example, chicken. So chicken is one part and the other part is related to these species. This is just one example. We don't want to talk about a specific characteristic of these species, because as soon as you change the topic, like to say, for example, in terms of beta globin gene, which one is the most similar, then maybe the arrangement would be changed. Or in terms of, for example, our eye vision, then again we can change the place of them. So for example, when we reach this part, again we subcategorize them into two categories. One category is related to mice and rats, and the other ones, as you can see, this category. Then, for example, if we ask questions like, for example, cow is more similar to human, or for example, rat, in this scenario that we have for this picture, because we don't know exactly which characteristic that we are talking about, which similarity we are talking about. But anyway, based on this picture, we would say, okay, cow is more similar because we can find the root here. You see, it is inside this subcategory. So based on phylogenetic trees, we can also answer these questions easily. And when we have unrooted ones, as I said, we don't have initial point, but these trees are very useful in order to just pick one species and compare it with other species like right away, without considering the root of them. Like for example, when we see human here and another species in another part, based on the distance, based on the branches that we have, sometimes it's easier to see it by having such unrooted phylogenetic trees. And as I said, sometimes the length of these lines are important. In this example, they didn't show such a thing because all of them we can see they are pretty much the same. But in some unrooted phylogenetic trees, that's not the case. So Now you already know what we mean by phylogenetic trees, but how to construct them? There are so many methods in order to construct them. The one which is inside your course syllabus is UPGMA, and we will talk about this one. This method is using distance metrics. So first, let's see how we can define a distance matrix. The value of each cell can be calculated by the inverse of scores obtained by pairwise sequence alignment. So one way is to calculate it using the inverse of the scores. We will practice it in the weekly assignment. This is not always the case that we find the values here using the inverse of scores, but this is one approach that they are using frequently. So we will practice it together later. But in this example, as you can see, they are given to us. And we notice here pairwise sequence alignment. It's not like multiple one. It means that 2 by 2 we are comparing them in order to find these scores. Like for example, G1 and G2 here, maybe it was the inverse of the score of aligning G1 with G2. And as you can see on diagonal, G1 together, the score of aligning is 0 here. If it was the inverse, maybe it was not the case, you see. So I will explain in the weekly assignment how we can deal with that. But this is always 0. It means that whenever we talk about diagonal, the distance between the same nucleotide or the same amino acid, we consider it always 0 because they are the same. So it means that when the score is higher inside the distance matrix, it means that they are more different. So if the score is smaller, then they are more similar. So based on just looking at it, we understand. But if you remember for score of aligning, when the score was higher, then it was a good thing because we say, okay, this is a score of match maybe. But when we talk about inverse, it means that, okay, when you inverse the number, obviously the scenario changes. So smaller would be bigger and bigger would be smaller. Now let me talk about this method by an example, because when you see an example, the method is very easy to deal with. So first thing we do, if we have the distance matrix, so this is a distance matrix now. Now, what we do? Choose the first cluster by finding the minimum distance, because the goal is to finally have such a graph, so to have such a diagram. So what I need to do is to group them into clusters. So the first thing we do is to find the minimum distance. So we don't consider the diagonal, we are talking about this part. Why I didn't give any information here? Because this is symmetric. Obviously here, if I have AB as 10, here BA would be 10 here as well. So it's good enough just to fill one part of the table for distance matrix. So what are the minimum values here? Here for BC and BD, we have minimum values. And this is a heuristic method. It means that not necessarily you will reach the optimum answer, but they are helpful. You know, we already talked about heuristic methods and how helpful they are. So it doesn't matter which one you choose. If I choose BC or BD, doesn't matter because it's a heuristic method. But obviously you don't choose 16 here, CE, because as you see, the distance between these two indicates that they are different. So the logical thing is to consider one of them. So BC, for example, let's consider BC in one cluster and let's see what happens. We should update our table first. Here, BC now inside one group, one cluster. So here, the scores that I find for this column and this row, they should be updated. The rest are the same. For example, for AD, if I have 8 here, it means that I had 8 in the previous one. Okay. For these ones, we don't have any change. Look at this one. If I want to put BC in one cluster and I want to compare it with A, what we can do is to find the average of them. The average of AB and AC, 10 plus 12 over 2. So you see in this example, this is how we calculate it. So 11 for this cell. Again, for BC and D, we do the same. It means that compare D with BC. So one by one, again, we do the same for all of them in order to find the answer. For example, D here, we have 4 for B, we have 6 for C, then we get the average of them, which is 5. And we do the same also for E, comparing with BC, we find the average. Now we have a new table. We should repeat the same procedure. It means that as soon as you update your table, find the minimum value inside your table. Here, this is 5. So it means that I consider now D in the same cluster with BC. Now, here you see, we consider B, C, D, all of them together. Now, what should I do in order to update the value for this one and this one? Because for AE, this is exactly the same as before. In all of the tables, you can see for AE, this is 7. Again, this is 7. But for this one, we should, again, update. In some books, or sometimes in some methods, they make this mistake to find the average from the first table. This is not necessarily a good idea, because when we already put them in, for example, B and C together, it's better to calculate the average between BC again with the new element. So when I want to find the distance between, for example, E with BCD, what do I do? In the previous table, I want to compare E with BC and D. So it means that I find the average between 15 and 12. Instead of going to the first table and calculate the average from with E, with B, C, D, because not necessarily you will reach the same answer, okay? So when I want to find the average, and also when you want to do it for your final exam or your weekly assignment, please make sure that you calculated the average for E with BC and E with D, not E with each element separately, so that we will reach these scores. Of course, because this is a heuristic method, that's the reason that scientists could have different opinions about it. We cannot say, for example, this is not true, but we have our own logic. And again, on the 3, I will explain you why this is the case. So now we have updated our table. 7 now is the minimum value inside our table. Now this is the time to consider A and E together in the same cluster. So you see, now we have AE and BCD. In order to compare them together, we have BCD and we have AE and BCD together. It means that here I should calculate the average between AE with BCD. I mean A with BCD and E with BCD, because in the previous one we don't have AE together. So A with BCD 9.5 and E with BCD. So get the average of 9.5 with 13.5 and we will reach 11.5, and that's the only one available. It means that you put all of them in the same cluster to finally reach your root here. So in order to construct it, how can I do it? There are 2 ways. From the beginning, consider, for example, we just put B and C together in the same cluster. So you can start from the leaves in order to construct your graph, your tree, phylogenetic tree, or you can start it from the root, that all of them are together. And first, for example, we check at this one. What are my subcategories? I have AE and I have BCD. Okay, AE will be subcategorized again into A and E, and finally I reach my leaves. So it's based on you, which one you prefer. I think from leaves to root it would be easier, because this is the procedure that we took from the beginning. Like first we consider BC together. So first you show that, then we consider BC with D, then we consider that, and you see, and finally we reach the root. It depends on you which one you prefer, but the trees that we are giving you are easy anyway. For extra reading, it would be nice to go through chapter 7 of the textbook, but I think for this topic and this method that we talked about, the slides are clear enough. You won't even need it for final exam to go through this chapter to read it completely, but it's nice to learn about it, to know what are the other methods, and you would know more about the details. Let me remind you also, this topic is not included in your midterm. It's related to your final exam, and we will practice with it in the weekly assignment for sure. Let me also deal with one weekly assignment today, and on Wednesday we will have more time to talk about profile HMM, and we practice with it before your midterm exam as well. So if you have any questions, please ask me. Otherwise, I will start the weekly assignment.